Good morning, students. Welcome to 11th Standard Chemistry video class. We are discussing Lesson 6 Gaseous State. In our last video class, we completed the topic Dalton's Law of Partial Pressures. In this video, we will start with the new topic Graham's Law of Diffusion. Graham's Law of Diffusion. Before starting with the topic, let me know what is diffusion and effusion. Gases have a tendency to occupy all the available space, which means wherever be the space available, that the space should be occupied by the gases. This is the property of a gas. When two non-reactive gases are allowed to mix, the gas molecules migrate from region of higher concentration to a region of lower concentration. This property of gas, which involves the movement of the gas molecules through another gas, is called diffusion. Effusion is another process in which a gas escapes from a container through a very small hole. Whenever two non-reactive gases are mixed, the gas molecules moves from region of higher concentration to the region of lower concentration. The gas which involves movement through another gas molecule is called diffusion. It is shown in the first picture. Here, non-reactive gases means they do not react but they will mix. It is to be given for diffusion. Next one, effusion. Gas molecules in a container which moves through a small hole is said to be effusion. It is shown in the second picture. Hence, these two pictures explains about diffusion and effusion of gases. Now, we will discuss law of diffusion, which is given by the scientist Graham. Therefore, it is said to be Graham's law of diffusion. According to Graham's law of diffusion, the rate of diffusion or effusion is inversely proportional to the square root of molar mass. This statement is called Graham's law of diffusion or effusion. Just now only we explained about diffusion and effusion. Again I repeat, the rate of diffusion or effusion is inversely proportional to the square root of molar mass. This statement is called Graham's law of diffusion or effusion. The mathematical expression for Graham's law of diffusion or effusion is given here. Rate of diffusion proportional to 1 divided by square root of m. Here the m represents molar mass of the given gas. Again I repeat, the mathematical expression for Graham's law of diffusion or effusion. Rate of diffusion is inversely proportional to square root of m, where m is the molar mass of given gas. Consider two non-reactive gases, namely gas A and gas B. For gas A, the Graham's law of diffusion is given by rate of diffusion of gas A, that is Ra is inversely proportional to square root of molar mass of gas A, which is given by Ma. It is mathematically expressed as Ra is proportional to 1 divided by square root of Ma. Similarly, for gas B, the Graham's law of diffusion is given by rate of diffusion of gas B, that is Rb is inversely proportional to square root of molar mass of gas B, which is given by Mb. It is mathematically expressed as Rb is proportional to 1 divided by square root of mb. Divide RA by RB. We will get RA divided by RB is equal to square root of MB divided by MA. It is given in equation 6.15. Again, I repeat, RA divided by RB, which is equal to square root of MB divided by MA, or otherwise rate of diffusion of gas A divided by rate of diffusion of gas B, which is equal to square root of molar mass of gas B divided by molar mass of gas A. It is the Graham's law of diffusion for two non-reactive gases, namely A and B. When diffusing gas are at different pressure PA, PB, it is given by RA divided by RB is equal to PA divided by PB into square root of MB divided by MA. It is given by equation 6.16. Here RA and RB are rates of diffusion of gas A and gas B. MA and MB are the molar mass of gas A and gas B. It is to be given for Graham's law of diffusion. Hence, we completed the topic Graham's law of diffusion. Next, let we discuss a problem based on Graham's law of diffusion. The question is given here. An unknown gas diffuses at a rate of 0.5 times that of nitrogen at the same temperature and pressure. Calculate the molar mass of the unknown gas. In the question, we have to calculate molar mass of unknown gas. The another gas is nitrogen, in which unknown gas diffuses at a rate of 0.5 times that of nitrogen. The solution for the problem is given here. According to Graham's law of diffusion, the rate of diffusion of unknown gas divided by rate of diffusion of N2 gas is equal to square root of M N2 gas divided by M unknown gas. Here the M represents molar mass. Substitute the values in the above equation. Here, as per the question, rate of unknown gas divided by rate of N2 gas is equal to 0.5. The molar mass of N2 is 28 gram mole power minus 1. For 1 nitrogen, the molar mass is 14 gram mole power minus 1. For 2 nitrogen, the molar mass is 28 gram mole power minus 1. So, it can be written as 0.5, which is equal to square root of 28 gram mole power minus 1 divided by M unknown. Squaring on both sides, we will get 0.5 the whole square is equal to 28 gram mole power minus 1 divided by M unknown. Here the 0.5 the whole square is 0.25. Rearrange the above expression, we will get M unknown is equal to 28 divided by 0.25. After simplification, we will get 112 gram mole power minus 1. Hence, the molar mass of the unknown gas is 112 gram mole power minus 1. Hence, we completed the problem based on Graham's law of diffusion. Next topic, deviation from ideal gas behavior. This topic explains how the gas molecules deviate from ideal gas behavior, which means when they behaves ideally, when they behaves non-ideally, it is explained here. The kinetic theory of gases, which is the basis for the gas equation, that is PV is equal to nRT. If any gas which obeys the gas equation PV is equal to nRT, then it is said to be ideal gas. If it does not obey the gas equation PV is equal to nRT, then it is said to be non-ideal gas. How the gas deviates from ideal behavior is explained here. Assumes that the individual gas molecules occupy negligible volume when compared to the total volume of the gas, and there is no attractive force between the gas molecules. If you compare the total volume of the gas, the volume occupied by individual gas is too small. Hence, there is no attractive forces between the gas molecules. Gases whose behavior is consistent with these assumptions under all conditions are called ideal gas. Hence, the gases which obeys the above assumptions under all conditions are said to be ideal gases. But in practice, both these assumptions are not valid under all conditions. For example, the fact that gases can be liquefied shows that the attractive force exists among molecules, which means liquefaction of gases shows that the attractive force exists among molecules. Hence, there is no gas which behaves ideally under all conditions. The non-ideal gas are called real gases. Hence, the real gases tend to approach the ideal behavior under certain conditions. The gases deviates from the ideal behavior are said to be non-ideal gas. Non-ideal gas are otherwise called real gas. Next topic, compressibility factor. It is denoted by Z. The deviation of real gases from ideal behavior is measured in terms of ratio of PV to N or T. This is termed as compressibility factor, which is denoted by Z. Mathematically, it is expressed as Z is equal to PV divided by N or T. It is obtained from ideal gas equation. It is the definition for compressibility factor, which is denoted by Z. Again I repeat, Z is equal to PV divided by N or T, where Z is compressibility factor, P is pressure, V is volume, N is number of moles, R is universal gas constant, T is temperature. Therefore, Z is equal to PV divided by N or T. It is to be given for compressibility factor. For ideal gases, PV is equal to nRT. Hence, the compressibility factor Z is equal to 1 at all temperatures and pressures. For these gases, the plot of Z versus P should be a straight line parallel to the pressure axis. Here, Z is nothing but compressibility factor, P is nothing but pressure. Therefore, in the graph, x-axis is taken as pressure, y-axis is taken as compressibility factor Z. Hence, for these ideal gases, the plot of Z versus P should be a straight line which is parallel to x-axis or pressure axis, which is shown in the graph. When gas deviates from unity, for all gases at very low pressures and high temperature, the compressibility factor approaches unity and they tend to behave ideally. For all cases, in order to behave ideally, the condition is very low pressure and high temperature. Again, I repeat, in order to behave ideally, the condition is very low pressure and high temperature. At this condition, compressibility factor Z approaches unity and behave ideally. The plot of compressibility factor versus pressure for some gases are shown in the graph. Here we are having the plot of the compressibility factor Z versus pressure P. It is explained for hydrogen gas, nitrogen gas, methane gas, helium gas and carbon dioxide gas. In this graph, the line which is parallel to pressure axis or x-axis Z is equal to 1 for ideal gases. In this graph, above Z is equal to 1, we are having Z greater than 1. That is, real gases show positive deviation. Below Z is equal to 1, we are having Z less than 1. That is, real gases show negative deviation. Again, we are having one more graph which shows the compressibility factor Z versus pressure P at different temperatures for nitrogen gas. Here in this graph, the deviation occurs at different temperatures. The violet color line indicates at the temperature of 220 Kelvin. The green color line indicates at the temperature of 273 Kelvin. The yellow color line indicates at the temperature of 327 Kelvin. Finally, the red color line indicates at the temperature of 400 Kelvin. Hence, we completed the plot of compressibility factor versus pressure at different temperatures for nitrogen gas. Hence, in this video, we are having the following questions. First one, explain Graham's law of diffusion. Second one, give the differences between diffusion and effusion. Third one, what is compressibility factor Z? And finally, give the conditions for gases that deviates from ideal gas behavior. Let me stop up to this topic. The remaining that we will discuss in our next video class. Thank you.